Okay, good morning, everyone. Hopefully you're here to learn about developing in Python on Red Hat platforms. So I'll start with a quick introduction, who I am. So my name is Coghlan. I'm a C Python core developer. I work for Red Hat on developer workflow tooling. And I'm also involved in the Python packaging ecosystem and developing interoperability standards there. Co-presenting with me today is Dumpleton, who's the creator of the ModWizgy Apache plugin to run Python applications. And he's an OpenShift developer advocate for Red Hat down in the Asia-Pacific region. And so the slides today will be available after the conference. And there's a resource section at the end of that with links to various things. And so, yeah, so that'll, you don't need to take notes all the way through. So as to what we're going to be talking about today, mainly we're going to be focusing on how we recommend developing Python applications for Red Hat platforms across 3 different areas. So initially focusing on network services, then looking at what's involved in developing that applications that aren't themselves network services, and then the use of Python in system administration contexts and that kind of thing. Then at the end, we're going to look at some significant transitions that are currently going on in the Python ecosystem. So the ongoing migration from Python 2 to Python 3 being a big one. Some changes that have been happening when it comes to modernizing the Python 2.7 network security stack. And then also some changes that were made upstream in the standard python.org releases around how HTTPS certificates are handled. However, to start, we're going to be looking at Python for network services, and I'll hand over to Graham for that.
Thanks, Nick. OK, Python for network services. So what I mean by network services here is essentially anything you want to run which is going to be accessible beyond the system it's running on. So I was sort of like drawing a line there at things though which are running on a system to support that system. So I'm not talking about management applications or monitoring applications and so on. So I'm talking about things like web applications, be it your own monolithic web application, whether you're doing microservices or anything like that, or if you're bringing in a vendor application and want to run that. Also things like databases, whether you're using traditional SQL databases or NoSQL and so on. Now, for some reason, our slides are black on this laptop. I have no idea. There's meant to be a lot of color in that slide. So for network services, the solution that we recommend is OpenShift. And what OpenShift provides you is a containerized environment, which is going to provide you a level of isolation for your application. So the idea with the use of a container is that that application is not going to be able to be accessed from other applications running on the same system, or if you're running multiple different users on that system, they would not be able to access. Everything's all compartmentalized off, and that's the beauty of having containers. The other thing with using OpenShift is that OpenShift is designed for running across a cluster of machines. So by using OpenShift, you're set up such that if you do need to scale up your application in the future based on demand, then you've got that capability to run up multiple instances of your application on the same host, or you can start to spread it across multiple machines in a cluster. OpenShift has been around since 2011. And we've got sort of, in that time, it's been regarded as what's called a platform as a service when you talk about all the different cloud service types. So it fits there in the middle. The idea that you can essentially bring your application code, you just give it to OpenShift and it will go and deploy it. One thing that we've done in the last year and a half is that we've gone effectively and completely rewritten OpenShift. So if you are familiar with it and you've used it before, what you have used is what we call OpenShift 2. But we've gone and rewritten that now, and we've brought out OpenShift 3. And the difference is that we have essentially taken what we were using in the way of containers and replaced the container runtime we were using, which is an own internal system that had been built, and replaced it now with Docker. Docker itself, though, does not provide all the sort of functionality and nice features that we need in this sort of environment. We need to add on more security around things, so and orchestration and scheduling. So we add in Kubernetes on top of Docker for orchestration and scheduling, and then OpenShift itself adds in other components for handling better security, multi-tenancy, automated builds and deployments, as well as load balancing and external routing for actually making your applications visible and public out there so people can access them. Now, I mentioned that it's regarded as a PaaS, but one of the things we get from using Docker is that with Docker, you can actually now bring in your own images from outside. You're not restricted to using images which have been built inside of OpenShift. So you can pull down stuff from on Docker Hub, or you can be building on your own box and push those Docker images up in there. So in some respects, OpenShift is now more than just a PaaS. And if you add on top of that OpenShift itself also provides images in there for databases, or you could get an image from a vendor for their application. So for example, CrunchyDB has Postgres databases. You could bring that one in as an external one. So it also has an aspect there of what you would know as software as a service. So rather than being just a PaaS, it now actually covers all of these different sort of free cloud services of infrastructure as a service, platform as a service, and software as a service, but in a containerized environment. So it is now much more than a PaaS, and it's what we sort of like to call it a container platform now, because it's much more complete in what it can do. As far as Python and what we're interested in, it doesn't matter sort of what Python application you're using. If you're doing web applications, you can use Django, you can use Flask, you can use Pyramid or any of the other WSGI frameworks. If you're into async systems, Twisted, Tornado, or if you're into async I/O, we're available now in Python free. You can also use that. And as far as deploying it, it's a simple matter of telling OpenShift, if you're going to use the web console, what Python version you want to use, and give it a name for your application, and then you're just going to tell it where your source code repository is. What OpenShift will do is pull down that source code repository, and it will incorporate your application code into a Docker base image. That Docker base image provides all the Python runtime environment. So the particular Python version you've installed, and there'll be a whole bunch of system packages there which support you being able to install common Python packages out there. So libraries such as libxml, graphics rendering libraries, and things like this. Things that when you do a pip install of a package are needed to be able to install those packages. And once it pulls down that source code, although I've mentioned installation of package, OpenShift's actually going to do that for you. So it will identify that you've got a requirements.txt file in that core source code repository, or you're using a setup.py which has dependencies listed in it, and OpenShift will go and install those dependencies for you as part of building that image for your application. It'll also go and set up various scripts inside of there, such that later on when you go to deploy that image and run it up, the web server will be automatically set up for you. So you don't need to worry about any of that. OpenShift will handle it all for you. If you don't like web consoles, you can also do this from the command line. It's just a case, again, of pointing it at the particular Python version you want and telling it where the source code repository is. And stressing again that you don't need to do anything. OpenShift will sort it all out. You don't need to know how to build a Docker image. Okay? Now, the magic that is used to do this is a thing called source to image. And this is an illustration of how that sort of system works. We have a Docker base image which already has all the system packages installed, has the Python runtime in there for the particular version, and also has in there these couple of scripts, which are the builder scripts. There's two different scripts. There's one for the build phase, which is the thing which is going to install all of those packages that you require. If you're using Django, it'll go in there and collect all the static files together for you such that they're a part of that image, all done for you. And then it will have a start script, which is the thing or run script, which is going to then start up that web server for you when that image is deployed. Key, though, is that this source to image, although it is integrated into OpenShift, it is a separate project. You can use it independently of OpenShift. So OpenShift has these means in here for automated builds and deployments, but if you've got an existing continuous integration and continuous deployment pipeline using Jenkins or whatever, then you can still use source to image outside of OpenShift to generate that Docker image. Do your testing independently in that existing pipeline before you then actually push that image into OpenShift, and OpenShift will then still deploy it. So it is a separate component, it is a separate project, and you can use it in that way as well. And as a consequence, you can just use the command line to do it. So source to S2I is the actual command line tool, which you can use to do that. We have, for that, base images for Python 2.7.3.3.3.4 with 3.5 coming. That's currently going through testing at this point in time. And you're falling back on that. If you are using a RHEL subscription, you can get access to the RHEL operating system variants. If you're using OpenShift Origin, which is the upstream, you've got access to CentOS versions, or you can use those in the main one as well if you want. The other thing with those base images, though, even if you're not interested in source to image itself, there's still existing base images you can use yourself. So if you are familiar with building Docker images yourself and you feel that you have a requirement for a very custom image, so you want to install these extra system packages because you have some special requirement for some obscure science package because you're doing some really weird stuff with Jupyter Notebook, for example, then you can create derived images from these Docker images as well. And there's two ways you can go with that. You can create a new S2I builder which has the extra packages in it, and then you can just use that in OpenShift. Or you can just use normal Docker file to build up your own image total. And so in that case, you'll be installing all the packages yourself for Python and setting up the WSGI server. And so you can take those two different paths. If you're using OpenShift 2 already, anyone here using OpenShift 2 already? One, I see. There are enough differences between the two environments that you're going to have a measure of porting to do to get it from one to the other. At the moment, there is porting guides being put together, but it's not going to give you an automated solution to go from one to the other. If you do have substantial investment under OpenShift 2 and you feel you'd like more assistance than just the porting guide, then we are interested in hearing from you and getting feedback on what you would like to see. There are a couple of options there with being able to provide a custom source to image builder which more closely mirrors how things worked in the old OpenShift 2. And we can sort of augment that with templates for deploying common scenarios with a web app and database and so on to try and aid that transition. So if you are interested in that, we do have a booth over in Moscow and West. In the Community Central, if you turn up the OpenShift Origin booth, I'll be there a lot of the time. And we've got other developer evangelists there who can sort of help you with working out how you may handle that transition. As far as OpenShift in the past, there was essentially two ways you could use it with OpenShift 2. We had OpenShift Online, which was the public path, or you could get OpenShift Enterprise, I think it was still called at the time, and you could install that on your own machines and look after it yourself. In OpenShift 3, we have a range of other options now as well. There is OpenShift Container Platform, which is what we used to call OpenShift Enterprise, which is if you want to install it yourself and manage it yourself, you use that. At the other end of the spectrum, again, you still have OpenShift Online, which is where Red Hat sets it up, manages it, and you just use it as a user. That system, though, is shared with other users. If you don't like the fact that you've got other users on the same system, then we have in between them OpenShift Dedicated. That is, again, a system which is like OpenShift Online. Red Hat will set it up and manage it for you, but it's dedicated for your particular company's use. For development and testing, you've got a couple of options there. There's OpenShift Container Local, which is a self-contained virtual machine using VirtualBox. You can run that up on your own laptop. You can use it to experiment with OpenShift on your own machine, or you can use it as part of your development cycle. And we will have OpenShift Container Lab, which is the same as OpenShift Container Platform, but we provide that in a way that you can use it in your own development testing internally to your company, not in production, and we'll just treat that a bit differently in terms of how that handles with subscriptions and so on. So they're the options for network services. So we're going to move now back to Nick. And Nick's going to talk about when you wouldn't use containers and how you can put some of the things together if you aren't using containers, and also some of the other issues that come up with Python.
Thank you, Graham. So, Python for applications. So we're going to start by saying, okay, so we're recommending containers as the preferred option for network services. However, there's some interesting problems with that. So container support at the moment is, for rich desktop applications, there are still some limitations. They're being worked on, but at the moment, it's probably not, it's definitely an experimental R&D type activity at this point, rather than something you're going to be using for deploying your custom desktop apps today. Some particular applications and services may really want bare metal I/O performance. If you're trying to wring every ounce of performance out of your hardware, while folks are working actively to remove the performance implications of container abstractions, that's still a work in progress, and people are definitely working on that, particularly in the telco area, but there's still more to be done there. And then in other cases, containers simply just give you more isolation from the system than you actually want. They do have mechanisms in there, particularly super privileged containers, that do give you full access to the host system, but it may require some non-trivial modifications to your application to make it container aware and actually let it work that way. And so Red Hat offers an alternative, and software collections aim to offer minimum viable runtime isolation. And in particular, a couple of the key things they do is they let you put additional binaries at the front of the system path just in the region where the collection's enabled. They let you add additional shared libraries to the dynamic linkers path. And there's a few other system environment variables that they let you modify. And essentially, you have an application that is running natively on the host, but just has some slightly different configuration settings. And so software collections for Python in particular, so number one, it lets you use newer Python runtimes on the operating system without impacting any of the system components that actually use user bin Python and rely on that being a particular version. The other thing it lets you do is it lets you use a common Python runtime across multiple operating system versions. If you want to use Python 2.7 on both RHEL 6 and RHEL 7, you can. If you want to use Python 3.5 on both RHEL 6 and RHEL 7, you can. And that's the last point there. It's the way to get Python 3 for Red Hat Enterprise Linux 6 and 7. We don't ship a system Python 3 on those operating systems. If you want to use Python 3 on RHEL, you need the Red Hat software collections. And so the versions of the software collections that are available, so they're available for Red Hat Enterprise Linux 6 and 7 via the softwarecollections.org upstream. They're also available for CentOS 6 and 7. And as Graham spoke about earlier, they're the basis for the OpenShift language runtimes for Python and for all the other language runtimes as well. And so as of the latest software collections release, which is 2.2, the base Python 2.7 version is Python 2.7.8. There's some additional Red Hat backports from later Python 2.7 maintenance releases that Red Hat's added on top of that. And then the most recent one is Python 3.5.1, and again with some additional Red Hat backports. We also still have in Red Hat Software Collections 2, Python 3.3 and Python 3.4, those collections are still there and will be for the life of the life of the RHSCL2 series. As new major versions RHSCLs are released, those older Python 3 versions will come to the end of their support lifecycle and get dropped off, and people will be encouraged to upgrade to the newer Python versions. But getting your language runtime is all well and good. You then need a way to build your actual application on top of that. And one of the things software collections bring to Red Hat Enterprise Linux that they've never had previously is they bring in Python virtual environment support. And so software collections let you run multiple runtimes, multiple language runtimes to share a system without conflicting with each other. What Python virtual environments do is they let multiple Python applications share a Python runtime without conflicting. And one of the beauties of virtual environments is they basically have no runtime overhead because all they do is they work by modifying Python's import path. And so it gives you an additional location to import from. It may optionally turn off access to the system import path, depending on how you configure them. And what this lets you do is it lets you cleanly isolate your application dependencies, that the things are there because you need them, from the system components or the software collection components. And so you can clearly say, these are the bits that are actually part of my application versus these are the system components provided by the platform vendor. And so then within the virtual environment, the tool provided to manage those application level dependencies is pip. And so the tools we provide to create these virtual environments, so within the Python 3.4 and 3.5 collection, you can use the pyvenv script or equivalently run that through Python's module invocation as Python 3-mvenv. And then provided in both the Python 2 and 3 collections is the version independent package virtualenv, which works slightly differently. It's actually the precursor that became venv in the standard library. And the key thing here is that these are not actually included in the RHEL system Python. We do not provide them in the base operating system. We only provide them in the software collections as a tool for building applications. And so when you have an application built this way, what you end up with is this model where the base operating system environment, the base language runtime, those are coming from Red Hat. They're defined by Red Hat. We say these are the things that we think should be included in this base environment. But then as an application developer, what you can do is you then use the virtual environment tools to define your virtual environment. Then on top of that, you use pip to say, these are my additional application level dependencies that I'm going to use in my application. And then at the very highest layer, you have your application itself. And the application itself, you can either choose to package that using the Python native formats and install that using pip as well. Or as the S2I builders in OpenShift work, you can say, I'm just going to install my application directly from source control and not actually turn that into a separately shippable binary at all. And so that then lets you have this clear layering in your application of, this is the platform I'm running on. These are all of the pieces of my application, even if I didn't write some of them. Like some of them are pieces you didn't write. You're just using a package manager or a dependency manager to bring them in and combine them with your application so you don't have to rewrite them from scratch. And so you're not copying all of this source code into your own source tree. And so that then lets you construct a layered application. Now, once you've constructed that, the question then is, how do you actually deploy it? Now, if it's a network service, well, the answer is you do all of this inside your container and then deploy the container. But if you're not using a container, then how do you get that into production? And I mean, you can just package all of this up in a zip file or a tarball and then plonk that onto your server. Your sysadmins won't like you, and your auditors probably won't like you either. And so very useful technique at this point is that what you can do is you can prepare an application RPM that has all of your entire virtual environment in it. And what that gives you is it means that you can integrate with standard system management tools. So all of your automation systems like Ansible and so forth will be able to deploy your application. And you'll also integrate with a lot of standard system auditing tools. And that you'll be able to say, okay, give us a manifest on what's on the system. And it will be able to say, well, this version of this application's here in addition to all the system components. And so one of the easiest ways to do that is you can create the application RPM directly. And you essentially just, by whatever means, create a full installation, including the virtual environments and the software collections in a representative system. And then you just take that entire virtual env and any other bits and pieces you need, like activation scripts for the SCL, and just combine all that into one RPM. The one downside of doing it that way is you're not necessarily taking full advantage of the RPM ecosystem and the tools that exist around SRPM, source RPM management. And so then your other option, which can be a little bit more work, but may be worth it, is to actually define a proper full source RPM and then actually do the build and deploy process and the creation of the virtual environment during the RPM build. Which of those two options you take is going to be situation dependent, but either one should get you most of the auditing and monitoring benefits. And in the second case, there actually are some slight issues with the way pip handles that case. We know it's not right. We know we need to fix it. But it is in metadata that shouldn't be, if you're using RPM to manage the components, the difference shouldn't matter because it relates to pip won't be able to uninstall it properly, but RPM will be handling the uninstall, so it doesn't matter. One thing to definitely keep in mind when building applications this way, the Python package index is not an app store. It is designed to make the barriers to publication incredibly low. There is actually a script that runs to remove list of list builders because there is a tutorial or a textbook somewhere out there that teaches people to upload list of list builders to PyPI. And yes, so we actually have a script to remove those. So anyway, so there's no pre-publication review. The publisher terms of service ensures the Python package index itself has the right to operate. It ensures PyPI mirrors have the right to operate. The terms of services themselves do not grant you the right to run or modify the software that you find there. That right is granted by the open source licenses that people apply to the things they upload. And then the other thing is that publishers can actually delete packages from the Python package index. Just because it's there today doesn't mean it's going to be there tomorrow. We do make sure they can't replace it with something else, but just because they publish it today, they're under no obligation to keep it there forever. And so if you're going to actually start building applications this way and use the Python package index to bring in dependencies, we strongly recommend the use of caching proxies, and we strongly recommend that you implement a component review process. So commercial supported options for facilitating that, things like JFrog Artifactory, Sonatype Nexus, recent versions added Python support. And there are also open source projects out there to help with this. So DevPI is a very popular Python-specific solution for this that has lots of good development workflows. And then there's also a Python plugin for the Pulp repository management system. And so the things you may want to check in a component review process, you want to check the licensing. If you're an exporter that transfers software internationally, you want to check your export restrictions. And you may want to check things like project governance, how a change is made to the project, who has access to it, all this sort of stuff. And then finally, one of the other big things to keep in mind at this point as an application developer, security monitoring response is now your problem. You can't just say that's an ops problem now because those application dependencies that you're bringing in with pip, security monitoring and response at that level is now your concern. It is something that you need to keep track of, and if, for example, something like requests, so very popular client library for HTTPS, if they issue a security update and you're using pip to install requests into your application, then you need to do a security update for your application as well. And so as a developer, this is something to become very aware of and make sure that you take it seriously. And that pretty much takes us to the end of the application development side of things. It's pretty much build those layered applications, get the runtime from the underlying platform. You don't want to get into the business of being a Python distributor. But then above that layer, define your virtual environment, use pip to manage your application level dependencies, and then use pip or source control for deploying your own application components. However, moving on again, there's another category of development that unfortunately doesn't fit either of our previous two categories, which is software collections aren't perfect either. And sometimes what you're actually doing is you're actually scripting the operating system itself. You're actually essentially building an add-on to the platform. And in this case, you really do want to be running in the system Python. Some of the platform bindings will only be there. They're not available in software collections. And the system Python's always going to be there. You don't need to say, oh, we need to get the software collection there first, and then the application can run. And so some of these kinds of system administration tasks, you actually do want to be running in the system Python. And so in that case, the versions you're going to be worrying about, so not on this slide is Red Hat Enterprise Linux 5. And in that case, you're going to be dealing with Python 2.4, which will come up in the next slide. But on Red Hat Enterprise Linux 6, system Python is user bin Python, and that is Python 2.6.6. However, the 6.6 refers to the oldest code that's in that version. It does have additional Red Hat backports on top of that. Similarly, Red Hat Enterprise Linux 7, user bin Python is the system Python, and that's, again, Python 2.7.5 with additional backports on top. And then on recent versions of Fedora, if you're poking around on the cutting edge, the interesting transition that's happened there is the system Python, so user bin Python still reverts to Python 2.7, but the system Python itself is actually user bin Python 3. And so operating system components like the package manager, the installer, and essentially everything you need to get the system up and running, SE Linux policy management, they're actually all running in Python 3 on recent versions of Fedora. So Python 2.7 still remains available in the Fedora repos, still binds to user bin Python, but it may not necessarily include all the system libraries that it used to. We do try and make sure that they're consistent, but yeah, it is the case that Python 3 on recent versions of Fedora is the system Python. And so that leads directly into some of the caveats and challenges of using the system Python that don't apply if you're using software collections or OpenShift images. And in particular, whatever the oldest version of the operating system you support is, those are the features of the system Python that you're restricted to. So if you are supporting RHEL 5, then you can't use any features added in Python 2.5 or later. And then the other problem you run into is that a lot of community-maintained libraries and frameworks will require newer versions of the Python runtime. Like they won't. We're starting to see now a lot of people dropping Python 2.6 support and setting Python 2.7 as their minimum version. And the number of projects that still support Python 2.4 or 2.5 is very, very low. And so what that does is it creates a conflict is if you're trying to still support Red Hat Enterprise Linux 5, where Python 2.4 lacks a lot of the Python 3 forward compatibility features, and you're also trying to support recent versions of Fedora, where Python 3 is the system Python, things can get difficult. And so this is one of the reasons where if you're doing system level management tasks with Python, one of the things you may want to explore is actually switching to higher level system abstractions like Ansible. So that's still Python under the hood, but it means a lot of the cross-distro compatibility problems become the Ansible team's issue to deal with, and less your concern as a Ansible user. So that's the three major categories of application that we wanted to look at today. So network services, use OpenShift, applications, use software collections, and then use the system Python if you really need to. And so with that, I will move on to the section of talking about some of the transitions currently happening in the Python ecosystem. And of course, the big one being the migration to Python 3. And also the major source of pain in using the system Python across RHEL, CentOS, and Fedora. And the critical things there is the Python 2.7 upstream support timeline. So the currently expected community end of life for Python 2.7 is, we're expecting that to go end of life in around January 2020. Plans are in motion for a thank you Python 2 in PyCon 2020. But in Red Hat Enterprise Linux 7, so the support lifecycle for RHEL 7 runs out to June 2024. So that has Python 2.7 as the system Python. So that will be around until at least 2024. However, we do expect community project support for the Python 2 series to start declining sharply post-2020, when that upstream support period ends. And we're already seeing new community projects that start today as being Python 3 only. So one I came across recently was the Coconut functional programming variant for running on Python. That's, again, a Python 3 project only. So the good news is that a lot of the changes needed to prepare for a Python 3 migration are actually just general refactoring enablement. So you want good regression test suites. You want to be using static structural analysis tools like Pylint. You want to be doing automated continuous integration where every change and even every change proposal is run through a battery of automated tests and analyses. And the thing about this is that it's not just about getting ready for Python 3. These kinds of changes just let you move much quicker in general, because changes that you were previously scared to make suddenly become not so scary. That you can, the refactorings that you would previously say, we can't do that, we might break something, you say, well, we did that, everything still passed, static analysis still says everything's okay, we're prepared to take that much risk. And that then enables, amongst other migrations, it enables the adoption of Python 3. So how to actually do that for applications and network services? So if you're currently using the system Python on RHEL 5, the fact that RHEL 5 doesn't have a lot of the forward compatibility features that were added in Python 2.6 and 2.7, it really is a significant, it really increases the complexity significantly. So if you can, you really do want to upgrade to RHEL 6 or 7 first, so your baseline Python is 2.6 or 2.7. If you are using the system Python and don't need to be, then your next step would be to try and get out onto software collections. So that once you're on the Python 2.7 software collection, then you'll have things like virtualenv and pip available. You'll be able to bring in a lot more of the porting tools that are there to help with adapting existing Python 2 applications to run on Python 3. And then from that point, there's some excellent guides upstream on the python.org website and in the core CPython documentation that cover how to take an existing Python 2 application and bring it into the common subset of Python 2 and 3. And then once you've got your application running in modernized, running in Python, the Python 2.7 software collection, then you can start testing it and trialing it in the Python 3 collections as well. And one of the things we do in Python 3 releases is the common subset of Python 2 and 3 can actually get bigger. And so, for example, one of the original design decisions in creating Python 3 was that interpolation was a text operation and not a binary one. And so Python 3 originally didn't have a syntax for binary interpolation. One of the changes made in Python 3.5 was printf-style string interpolation actually came back for binary data. And so you can actually use mod formatting on bytes again. And what that gives you is that actually means that is now a feature that was previously Python 2 only and is actually now present in the common subset of Python 2 and 3, so long as you're able to target Python 3.5 as your Python 3 version. For migrating system administration tools, again, one of your options there is to say, well, do we actually need to be scripting this ourselves? Is there something like Ansible we can use instead and deal with that at a higher level and more declaratively? we could potentially experiment with recent Fedora versions and see whether what you're doing still works with Python 3 as the system Python. But to be honest, Ansible's own current approach is that they just bootstrap Python 2.7 on Fedora and bring Python 2.7, and so Ansible itself still runs in Python 2.7, even with the system Python being Python 3 on Fedora. So, and then some other miscellaneous notes on migrating to Python 3. So the common subset of Python 2.6 and 2.7 and recent versions of Python 3, it's actually really large. It's not quite native code in either variant, but you can write code in that common subset that looks a lot like idiomatic Python 2 code. You can write code in that common subset that looks a lot like idiomatic Python 3 code. And with the aid of tools like Modernize and Futurize, a lot of the stuff that is legacy idioms from the 2.2, 2.3 era, and even 1.5.2 in some cases, a lot of that can actually be dealt with automatically. You don't have to do it by hand. And so you can get a version that runs quite happily in the common subset just by running a single script over your code base and then saying, okay, what did it do? And review some of those changes. And you can even do that file by file quite often. And there's utilities to say, okay, this has been converted, keep it compatible. And then incrementally work your way through your code base, bringing it up to modern Python 2.3 subset code. There are a couple of pain points that really are dependent on your particular data set and your particular workload, and current static analysis tools don't help too much in picking them out. So one is the fact that the fundamental difference between, or one of the fundamental differences between the Python 2 data model and the Python 3 one is Python 3 is much, much stricter that binary data and text data are not the same thing. And it requires you to model them that way in your application. And this is fine if your application is clearly, you can say, okay, everything's binary data, we only deal with binary data. And it's also fine if you're in the situation when you can say, okay, we never deal with binary data. Everything we deal with is always text. And those two are the simple cases. Where things can get tricky is if you're writing applications that live on the boundary and are needing to deal with file formats and network protocols, and you can't just push that off to a third-party library and say that's the library's problem. In those cases, you may have some work to do to separate out, okay, here we're dealing with binary data, here we're dealing with text data, and that can be a bit of work. But the end result is that you actually have a more comprehensible system for humans and future maintainers as well, not just for the benefit of the interpreter. And another a bit more obscure one is, so Python 2 is actually very permissive in letting you make comparisons between types. And so if you ask Python, is the string 1 less than the number 1, it will either say yes or no, depending on the memory address at which the integer type and the string type were allocated on that particular run. This is not particularly intuitive and it's not particularly meaningful, so Python 3 doesn't do it anymore. It just says that operation doesn't make any sense. Please give me a key or something. But what it does mean is if you have a list which has nuns in it, and you try and sort it in Python 3 will actually complain because none doesn't actually compare sensibly with anything else. And so that's the one case where people will sometimes need to go through and say, find places where they're doing that and stop. And so the other but one of the other things to keep in mind here is that there's a lot of companies putting a bunch of time and energy into improving the available automated refactoring and compatibility testing tools. If people have seen any of the information about like static typing and type hinting in Python, a lot of that's actually driven by this migration, because one of the things static typing or type hinting can help you do is it gives you much stronger static analysis. And if you have something that passes static analysis to Python 2, and static analysis in Python 3, then you're in a situation where you say, okay, that gives you a much greater confidence that a migration is going to work, even if your test suite coverage isn't that great. So one of the things that came out of the migration, though, is that when we switched our attention upstream to working on Python 3, the Python 2.7 networking stack got stuck back in 2010. And that actually turned out to be a problem. And so what happened upstream was one of the biggest rebases ever done in a Python 2.7, in a Python maintenance release, which was in Python 2.7.10, I think it was. We backported essentially the Python 3.4 SSL module to Python 2.7. And we did that for a bunch of reasons, and there's a link to the PEP in the Python 2.7 What's New documentation. And it was basically a bunch of network security features where we were actually holding back the security of the entire internet, which we figured was a bad thing for us to be doing. And so what it did was it rebased the SSL module in Python 3.4 implementation, and it brought in things like server name indication support, much better SSL configuration. You could actually explicitly request TLS 1.x. You actually had access to system certificate stores, so you could find the system trust space. And so yes, so this turned out to be a really important thing to do. And so that is available in Red Hat products. So as of Red Hat Enterprise Linux 7.2, it's in the system Python. So all of the Python 3.4 and Python 3.5 collections naturally have this by default. And then in the latest software collections release, this was the biggest update made to the Python 2.7 collection. So it actually has the rebased SSL module in it. And so if you're using the latest versions of the RHEL products, you'll also be getting the latest version of the Python 2.7 SSL library and the security of the internet. Well, thank you. Unfortunately, this was not without its risks, and this was the biggest concern with it, and one of the reasons why it took quite some time to propagate out through the system. The rebase changed several private implementation details. And unfortunately, it turned out that some popular third-party libraries had been using those internal APIs instead of coming back to the core development team and saying, hey, can we have a public API for this that you properly support, please? And so the backports into Red Hat Enterprise Linux and into Red Hat software collections do offer greater compatibility than upstream. Like upstream just straight up said those APIs aren't there anymore. The backports do provide an emulation of those APIs to try and keep these third-party libraries working. That said, it is an emulation, and so testing before upgrading is still recommended, and then report problems through the usual Red Hat support channels. So yeah, so we do think that's an important upgrade, but it's unfortunate these libraries were using these external interfaces. The final one I'll talk about today is defaulting to HTTPS certificate verification. So this is an interesting question around what does HTTPS actually mean? And not in terms of what do the letters stand for, but what do people think it means when they see it on a URL? And so Python's historical answer in the standard library was that all HTTPS means is it's a HTTP connection with SSL TLS enabled. That's all. Doesn't imply anything about checking certificate validity, doesn't imply anything about checking the identity of the remote host. You go to most developers in 2016, and they're not going to say that that's what it means. They're going to say what their browser says it means. And what a browser says it means is, OK, yes, it's a HTTP connection with SSL TLS enabled, but they also expect you to check the certificate's valid. They also expect you to check that, yes, this certificate matches the host I'm trying to talk to. And so, again, one of the more controversial changes made to Python 2.7, and even controversial within Python 3, we switched the standard library HTTPS clients to actually do certificate validation. And what this effectively does is it turns a previously silent security failure where you're accepting a certificate that is not in fact valid for the connection you're trying to make, and it turns it into a noisy connection failure. And we do provide ways to turn that off and say, no, 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 I really do mean to let this connect. But a lot of those mechanisms require application updates. So this creates potential problems. You may be dealing with self-signed internal certificates. You may be dealing with certificates that have expired, but you know they've expired, it's still valid, it's going to get replaced soon, and right now you just need to connect to that server. And you can also just run into the case where the certificate is signed, it's perfectly valid, but it's signed by your internal CA, and the system you're currently using is not configured to trust the internal CA. And so these are real problems. You can't just deploy this change willy-nilly. You actually need to take into account the state of the certificates you're using and that sort of thing. So in backporting this change to Red Hat, we actually did it slightly differently from the way Upstream did. And we actually have a file-based opt-in to configure the behavior. And it's a config setting in a file. There's a knowledge base link that gives all the details for how this works. And so you can opt into this automatic certificate verification, but it's still off by default because there are people with systems where they're relying on this ability to access self-signed certificates, to access and to not necessarily have the current system configured with their internal CA details. One thing people will find is if they try to use the Python 3.5 collection, this does use the default upstream Python behavior where it will not make invalid connections unless the application itself tells it that's okay. That said, specifically for the Python 2 series, there is an implemented change upstream in Python 2.7.12 that implements a global opt-out setting specifically for Python 2.7. So these opt-out settings don't exist in Python 3 or any version of that. But they do exist in Python 2.7.12. And so, yeah, and the relevant PEP details, again, are in the Python 2.7 what's new documentation. And so, yeah, so those are some potentially disruptive transitions that we want people to be aware of, that these are happening. We are taking steps to help make them easier for people to deal with. And so happy to hear any questions people have about those, either now, where I think we have a few minutes, or in the corridors after. I'm here for the rest of Summit. So thank you very much.